Welcome back to this second part of the Prince efficiency model video series, mini-series. So in the last video, we looked at the model that Prince suggested in 1955. So what he did is he took the Trivich-Flinn model that considers which photons are absorbed and also how much thermalization we have in the generation of the carriers. And he extended it by this fill factor model that I showed in the last video. And so the fill factor means you have to look at the short circuit current, the open circuit voltage. You have to look at, for the given IV curve, what is the maximum power point, so how much power can be extracted. And then this maximum power that can be extracted is divided by the multiplication of U open circuit times I short circuit. And that gives you the fill factor, and then the efficiency of the Prince model is the Trivich-Flinn efficiency multiplied by the fill factor. And I showed you in the last video the very simplified diode model. And this is actually a very ideal model. And already in the early 1955 paper, Prince suggested a more elaborate model that is more realistic in terms of how solar cells behave. And that is what I call the extended equivalent circuit model. So it has again this extended model, this diode here. It has again the constant current source, but additionally 2 resistors are added in. And this is, first of all, this series resistance. Series resistance happens within the device. If you are moving carriers, you have a certain series resistance. And also externally, if you're connecting your solar cell, you might have series resistances. So there's definitely going to be some series resistance in the model, or in your solar cell, and therefore it also needs to be in the model. And also this parallel resistor here, often called also the shunt resistor, this takes into account that you might have some current flowing, not going through the external circuit, but actually shunting through your solar cell itself. And so Prince already suggested in 1955 to extend the simple model by these 2 resistances in order to describe it more correctly how actual real solar cells behave. Now, if we want to put up the current voltage model here for this circuit, then we can first of all consider the total current I again. That is the same current that goes into the resistance here. And now this current I is the photo current that is coming from here, minus the diode current that is going through the diode, minus the current that is going through this parallel resistance, the shunt resistance. And the current that is going through here is actually given by the voltage that we have over the diode, I called it UD, divided by the resistance of this parallel resistor. So the larger this resistance is, the less current we have that is shunting through the device. So a very large resistor is here actually a good device, because then we have little current going through here. Okay, then we can again proceed with this in order to put in the diode current. And the diode current here is given again by this model where we have the diode voltage divided by the ideality factor N times the temperature voltage -1. Now we have to change this in a sense that the voltage U on the outside is not the same as the diode voltage, but the diode voltage is given by the voltage U here plus actually the voltage through the resistor. So we have a voltage drop along this direction. So this diode voltage is Rs times I plus the voltage U. And that is what is put up here in the exponent. And also the diode voltage needs to be put in this position. So we have here the voltage plus Rs times I over Rp as the current that is flowing through this resistance. And so this is the IV curve here of this extended equivalence circuit. And you can see that this is actually, this has the current on this side, on the left side, the current I, but also on the right side, we have the current I here and the voltage U. So in order to solve this, we are going to solve it numerically in order to determine what the IV curves looks like if we have this IV characteristic for our extended equivalence circuit. So let's look at how this is implemented in MATLAB. Here we have the MATLAB script in order to calculate the IV curve for the extended model. And I'm again calculating for voltage values from -1 volt to 1.2 volts. Here I again have the ideality factor of 1.5, the temperature voltage of 25.9 millivolts. I'm assuming a reverse bias saturation current of 1 picoamps. And I'm assuming a photocurrent of 1 amp here. I'm now putting in a series resistance of 0.1 ohm here and a parallel resistance of 100 ohm here at this position. And now I want to calculate, first of all, what are the currents for the voltages U I've given here. And this I do by defining the function. This is what I call function 2 here for the extended model, and I want to calculate as a function, or I want to calculate the value of I, and I do it such that I do that I find the zero of this whole. This is the whole equation for the extended model current, and I subtract the current that I want to calculate. So we saw just on the slide that the current I here is equal to everything we have here. And in order to now do it numerically, I subtract on both sides of the equation the I. So I have 0 is equal to the whole current equation minus I. And then in MATLAB, I search for the 0 value where this equation is fulfilled by putting in the function name and doing an initial guess for the current. And my initial guess is just that it is half of the photocurrent that I defined up here. So 0.5 amps is my initial guess for the current. And then this can run through and I can plot the current. I will just run this section here. And you can see now here what this IV curve looks like. So it looks somewhat similar to the last IV curve we had. Let's just add a couple of more curves in order to see better what is happening. So let's, for example, say we take here just the series resistance that is very small. So I just add many zeros here. And I will plot this into the same graphic, but in red. So that was the original, or let's also do this very large here, the parallel resistance. So if we just plot this now into the same graphic, then we see that the curve actually is quite similar. We have only a bit of difference here. Let's zoom into this by limiting ourselves to positive Y values. Okay, so here we can see what the difference of the curves is. So the red curve is the same that we were looking at in the last video. If the series resistor is really, really small and the shunt resistance really high. And we see for the extended model, we get a curve that is actually bent a bit more. So let's look at some other value. Let's, for example, put here instead of 0.1 ohm, what I had initially, let's put 0.5 ohm, for example. And let's go back to the 100 here and run it. I'm running it in red again now, but we can distinguish the two curves because this is the new one here. And you can see if I have now this higher series resistance and I have the same value as for the blue curve for the parallel resistance, the series resistance causes this, this change here of the curve to the left side. And if I now look at what happens with the parallel resistance, if let's go back to 0.1 ohm and put here 10 ohm instead of 100 ohm, and I will plot it in green now so we can see it better. So this is what the curve looks like coming from the blue curve. We have the same series resistance, and now we have a higher shunt resistance. And you can see for the higher shunt resistance, we actually get more of a bending in the front part of the curve here. So the green curve is the effect of the shunt resistance, and here the red curve compared to the blue curve is the effect of the series resistance. So for the we get here for the shunt resistor, it's more bending like this. And for the series resistance, it's in the back part, we get an additional bending in. And then we can have any combination of the two. So I will just go back to 0.1 and 100. And let's plot it in black now so we know where we are. So now I'm back at this original curve here I had. Okay, so if we have now this extended model, we can proceed as before, that we now look at the power and the maximum power point. And the power is again found by multiplying the voltage by the current. And the graph looks as shown here. So if we multiply the voltage by the current, then we get this graphic here where we again have a maximum value. And the maximum value this time I only simply found by looking at the different values I calculated. From U times I is the power, and I just found the maximum value of these and noted what is the index of the maximum value, and then defined my maximum power point voltage as the voltage as this value. The maximum power point current is the current at this index of the maximum power point that we defined up here. And this is a simplified method. If you have quite closely spaced values, that this will give a good approximation. Alternatively, you can also start with coarser placed values and then in the region of interest do a finer calculation of the power values in order to get closer to the actual maximum of the power. Okay, and so then this is this maximum power point is plotted into the graphic here. And I actually proceed by then also plotting a graph as I was just showing you in the last video also. So this graph then shows the IV curve. It shows what the Trivich and Flinn efficiency is, multiplying the open circuit voltage with the short circuit current. And it also shows what the Prince efficiency is, considering the fill factor then additionally as this dark blue area here. And I actually also calculated what the fill factor is by just finding the short circuit current and the open circuit voltage, and then calculating the fill factor by dividing the power at the maximum power point by the multiplication of the short circuit current and the open circuit voltage. And for this case here, we see that the fill factor is 75%. So the fill factor in this case here is 75%, and that is what is also plotted here then. Okay, let's go back to the slides. Okay, we have just seen in the MATLAB code that for this extended model here, we get an IV curve as, for example, shown here. And then for this IV curve, again, we can proceed to calculate the power by multiplying U times I. We can calculate the maximum power point, so the power at the maximum power point, and also what the voltage and the current are at the maximum power point. Then we can calculate the fill factor from this, and the example that I'm showing here actually has a full fill factor of 67%. So it depends on what the IV curve looks like, what the fill factor is. So here I put in values such that I have 67% fill factor. And finally, we can then again combine the Trivich and Flinn model that we are seeing here with the 48% efficiency and this extended diode model that Prince suggested with a 67% efficiency. And for this case, we get an overall Prince efficiency, maximum efficiency of 32%. So if we have, of course, a smaller fill factor, then this efficiency value is going down. And that is why the fill factor is such an important characteristic. And even though this model is not widely known as the Prince model, the fill factor is used everywhere. So if you are looking at IV characteristics of solar cells, one of the important questions is always, what is the fill factor? Because the fill factor determines how much of the solar efficiency can be used, actually can be utilized with an external load. And therefore, one aim in solar cell research is to increase the fill factor. So it's always reported of what is the fill factor of a given solar cell that has been investigated. Thanks for watching.